tell me where you want to start.
Well, let's just start from number 1.
Okay. A work problem. Wow, they do not make it easy, do they?
No, they do not.
All right. What did I say when you had work problems? What's the first step?
RTW? Returns.
What you want to do is figure out how much work each machine can do in 1 minute.
Okay.
So one machine, we'll call it A, can do how much in 1 minute?
You can do one machine can make 7 levers in 1 minute.
Okay. How about the other machine? We'll call it B. What can it make per minute?
Per minute, it can make 5 levers.
Now, let's go from there. That's always my first step, is to figure out how much work you can do on a unit basis. And it wouldn't matter if that's at 5 hours and that's at 8 hours. I would figure out how much they could do per hour. So whatever time frame they give you, that's what you use for your unit basis.
So minutes, we do minutes.
Right. Okay, the second machine began making levers 3 minutes before the first began. How long will it take the two machines together to finish making 219 levers? Well, first of all, let's make this a little simpler before we attack the more complex version that they've asked us. How long would it, if they both started at the same time, how long would it take both of them working together to make 219 levers?
Wait, what do you mean? I'm sorry.
Let's ignore their question for the moment, and let's present our own question. Assuming they started at the same time, how long would it take to make 219 levers? How many are they making each minute working together?
Working together, they're making 12 per minute.
So 219 divided by 12 is equal to what?
Catch it. That's 18 or so.
Okay, so that's how many minutes it would take if they were both working together to make 219 if they both started at the same time.
Yes.
Well, the problem, they don't start at the same time. The second machine began making levers 3 minutes before the first machine. So the second machine is 5 levers times the amount of time, right? Times the number of minutes. Well, its time is t plus 3, if t is in minutes.
So it's already made 15 levers?
Yeah, at time 0, it's made 15 levers because it started 3 minutes early, and it makes 5 levers per minute. Well, the amount of levers that the first machine makes is 7 times t. And together, they make 219 levers.
Yeah.
So I have an equation, 7t plus 5t plus 15 equals 219. That's one equation, one variable. I can solve that. What's the next step?
Okay. We gotta solve for t.
Right? What's the next line?
Solve t equals 204.
Perfect. And t equals 12 divided, or 204 divided by 12.
Yeah.
How many minutes is that? Is that an even number?
Yes. It's not even. It's 17.
Why would they not make it an even number? What is it?
17 minutes.
Exactly?
Yeah.
Oh, good. Okay, so now we can test it. So the time that the first machine took was 17 minutes, right? It's asking you how long will it take? Well, if 17 minutes is the right answer, the first machine produces 17 times 7 levers per minute, right?
Yeah.
So the first machine produces that amount of levers.
Okay.
The second machine started 3 minutes prior. So it's 20 minutes times 5. That's 100. Total 219. Right on.
Yeah.
All right. Let's go to the next one. I was going to say these don't get easier, but actually they do. That's as tough as it gets, number one, as far as I'm concerned.
Really?
I think so, yeah. I would say these do get easier. The only thing you need to remember about converting a complex number is this. A plus bi, that's the complex number, equals sum r times cosine of theta plus I sine of theta. So we got to take that complex number and put it into that format. Now, here's what you need to know. R is equal to the square root of a squared plus b squared, much like the Pythagorean theorem. And theta is equal to the inverse tan of b over a. And this is a little more complicated. If a is positive and theta is equal to the inverse tan of b over a plus pi, if a is negative. Now, that's pretty strange. You do not run into that until you get to polar. Notice that it's not what b over a is, it's what a is, just the denominator. In other words, if a is negative, then you're going to add pi to this. Always remember, inverse trig functions are angles. That is an angle.
Oh, really?
Yeah, always. You take trig functions of angles to get ratios. We do the sine of 30 degrees to produce the ratio of 1/2. But if we're taking inverse trig functions, we take the inverse trig function of the ratio to get the angle.
Yeah.
So in this case, we need to solve for theta. So we're taking an inverse tangent function. Okay? So theta is equal to the inverse tan of b, which in this case is -3, over a, which is 4. You see where I got that from the complex number?
Yeah.
What's your calculator give you for that?
Should go.
In degrees.
And the inverse tan of -3/4.
Uh-huh. going to be a negative angle.
Negative 36.87.
I'm going to round that off to 37 degrees.
Okay.
Just because I don't want to deal with all these decimals, I'll let you deal with them. Yeah, I think it's silly to force you to deal with all these decimals. But okay, now we have our answer. Well, not quite. What was r? R is the square root of a squared plus b squared. What is that equal to?
The square root, that'd be 5.
Yeah, good.
I didn't even like, I don't know.
I know. You recognized a 3, 4, 5 triangle is what you did.
Yeah.
Okay.
Oh, cool.
So the answer is 5 times the cosine of minus 37 degrees plus I times the sine of minus 37 degrees. In other words, once you solve for theta and r, you have your answer. Now, this might seem a little bit strange. I'm reluctant to erase this part here because that's the key part. What I have written there at the bottom. In other words, right here, you have to memorize that.
Okay.
Because you have to figure out what theta is.
Yeah.
Now, I'm going to erase that.
Oh. So, oh.
Hold on. We can back up if you need to. This is the answer.
Now I get this now.
This is the answer right there. Now, you might say, well, how come we don't figure out what the cosine of minus 37 degrees is and the I sine of minus 30? Let's go ahead and do that. What is the cosine of minus 37 degrees?
Calculate the cosine, negative 37 degrees, is 0.799.
What's the sine of 37 degrees?
Negative 0.602.
What were the decimals?
602.
Now, if you carry out that distribution, here's what you're going to get. 5 times that is 4. 5 times that is minus 3.
Yeah.
That's what we started with. In other words, the polar form of that complex number is expressed like that, without simplification, which is rare because there's not very many math problems that you don't simplify. But this is one of them. When you're expressing it as a polar trig form of a complex number, this is your answer. If you want to check that answer, go ahead and figure out what the cosine of minus 37 is and the sine of minus 37, and you get back to your complex number. Exactly.
Gotcha.
So these things are identical. This complex number, 4 minus 3i, is equal to this polar form right there. Now, you might say, well, why would you want to ever do that? Well, there's lots of reasons, and they all are higher mathematics. But there's tons of advantages of expressing this complex number in polar form. It's just that most of them are all higher mathematics.
Yeah.
All right. So, two cis 15. How can I write that in polar form? What does that mean?
Oh.
What's R?
Oh. No, 2 CIS 15.
Uh-huh.
2 cosine 15 plus, 2 times cosine 15 plus I sine 15.
Exactly.
Hey, so I have a question actually here.
Uh-huh.
What Mr. Bell said to do these things, he says like with the 2 and the negative root 2, we multiply those two things, and then we add up 15 and 45, so then it becomes negative 2 root.
Yeah, let's finish this.
Yeah, okay.
Because it's a multiplication problem. So this part I can write as negative root 2 times cosine of 45 plus I sine of 45.
Okay.
And now we can figure out all of this. In other words, we can figure out what complex number that is, and we can figure out what complex number that is, and we'll just multiply them together and see what we get. Now, when they say express the answer in rectangular coordinates, if we still have an I, then we're going to have to use the real and the imaginary. If the I goes away, we might have an XY coordinate system. I don't know what's going to happen yet. So let's do this. What is the cosine of 15?
The cosine of 15?
Uh-huh. Make sure you're in degrees.
Degrees.
What is it?
0.966.
966?
Yes, sir.
What's the sine of 15 degrees?
0.259.
What's the cosine of 45 degrees?
The cosine of 45 degrees is root 2 over 2.
Notice that by writing it as root 2 over 2 instead of a decimal, I lose all my round off error. Root 2 over 2 times root 2 is 2 over 2, that's 1. Whereas if you would have given me a decimal for cosine of 45 and then I would have multiplied it by the decimal root 2, I would not have gotten 1. I would have gotten 0.999 or something. I don't know.
Yeah.
But it would have definitely had round off error in it. Now, if I do the inner multiplication, whenever you have multiple nested parentheses like this, you want to do the inside first. Okay? Well, the right side becomes minus 1 plus I.
Yeah.
You see that?
Yeah.
And the left side becomes, what's 2 times that number? That's what it is. 2 times that number is 518. So it's I times 0.518. Okay. Now we've got this number, a complex number, multiplied by that complex number.
Yeah.
Well, we can certainly do that by foiling. I don't have any more writing space, so let me go up top here. I'm going to multiply that by that. I get minus 1.9. And I'm going to multiply that by that. So I get plus 1.9i. Then I'm going to multiply that by that. So I get minus 0.518i. And finally, I'm going to multiply that by that, and I get plus 0.518i squared. What's I squared equal to?
I squared is equal to -1.
Okay.
I squared is equal to -1.
Yep, that's correct. So now I have minus 1.9. I'm going to combine those two because they're like terms. So that's plus 1.382i. And then plus 0.518 times -1, which means minus 0.518. So now I have the number minus 2.418 plus 1.382i. That's what our answer is in complex format. Now, I'm a little confused that they want it in rectangular coordinates. Let's talk about that for a minute. In other words, what I came up with was a complex number. That number right there. Well, complex numbers don't have nice rectangular formats in X and Y. However, you can plot them on the complex grid. And the complex grid is a lot like the XY grid, only the horizontal is the reals, the vertical is the imaginary part. So if I want to plot that number, where do I start? What's the real number? What's the real part of that answer?
-2.418.
Okay, we'll call that right there. -2.418. What's the imaginary part?
1.382i.
So that point would be minus 2.4 comma 1.4 if I round everything off. And that's what it is on the imaginary grid.
Okay, gotcha.
Now I say I'm a little confused because it says it wants its answers in rectangular coordinates. Well, I don't think you can plot an imaginary number in rectangular coordinates. You can plot it in rectangular coordinates as long as you use a grid whose horizontal axis is the real number and whose vertical axis is the coefficient of the imaginary part.
Yes.
So I think we have the right answer, expressing the answer in rectangular coordinates. Well, I still think this is the right answer, minus 2.4 plus 1.4i. That's as good as we're going to get. And then graphing that, it didn't really say graph it, it just said express it. So we don't need the graph. But, I don't know, do you have answers on these?
Oh, no, we don't.
Okay.
That would be the problem, because last year, the last semester, we got an answer sheet, but we didn't get one this year.
Well, answer sheets are nice to have when you have complicated problems. Because if you cannot figure them out, sometimes the answer sheet will allow you to figure them out. So it's like, you know how most, well, maybe you haven't experienced this at Devlin, but most of my students have every odd answer in the back of their book. Just the odds. You have that also?
Yeah. Yeah.
When you get to calculus, guess what happens? They give you the answer to every question.
Oh, that's nice.
Well, there's a reason for it. That's because the answers frequently help you solve the problem. If you do not know how to do the problem, given the answer, sometimes you can go back and figure out how to do the problem. So that's why they give you all the answers in calculus, is because they're all hard problems. So you're always looking for confirmation that you did it correctly, and that's why I ask. In other words, when I say, do they give you the answers, I'm looking for confirmation that we did it correctly.
Exactly.
All right. Since we don't have answers, we can't confirm that. Let's just go to the next problem. Hold on a second.
Let's go.
Yeah, you tell me which one.
Yeah, let's do 4. I don't need to do 5, but I definitely need to do 6.
Okay, so we'll do 4 and 6. I'm getting good on these normal distribution curves.
Yeah, I feel like I'm getting better, honestly.
Yeah, I think you are also. So all you have to remember is these zones.
Oh, exactly, yeah.
What's that point right there?
That is gotta be 172.
What's the next hash mark I should make?
Make one. That would be 177.
This one would be 167.
Yeah.
Okay. Now let's break this into zones. What's zone number 1?
From 172 to 177. That's
No,
34.
from 167 to 172. What is that zone?
Oh, my bad. Yeah, that's 34%.
And from 172 to 177?
It's 34%.
All right, now let's look at the problem. They want to know which percentage lasts less than 179. So what's the next hash mark I should make?
Mr. John, can you hear me?
Just barely. We're getting some interference here. Go to your GoToMeeting, go up under audio, and make sure you have it set on telephone. Sounds like you're getting feedback. Now it's fine, right?
Yeah.
What happened was you had GoToMeeting set on use computer audio, and it started working a couple of minutes ago, and it produced feedback because you also had your phone. So when you start hearing that feedback, that means it needs to be set on either phone only or computer audio only. But only if your computer audio is working. Okay? Now, let's look back at this picture. What's this zone number 2?
13.5%.
That's all we need. Okay? What percentage of operations last less than 179? Well, first of all, what percentage of operations last less than 172?
50.
Plus whatever's in this zone
It's 34.
plus whatever's in this tiny zone from 177 to 179. In fact, there's 13.5 there. That goes all the way up. No, excuse me. That would go up to 182.
Yeah.
So we don't want 13.5. What percentage of this zone, hold on a second, I got this so small I can't see what I'm doing here.
Yeah.
Let's see, that's 177. That's 182. So I got 179 in the wrong place. Can you read my x-axis here? Okay.
Yeah, I can read it. Well,
That's 179. So that zone is 13.5%, right?
yes.
What part of that zone are we talking about?
Between 177 and 179.
Okay. What percentage of that zone is that?
5.4%.
It's 2/5. Notice the whole zone is 5 points. This is 2 points. I'm only going 2 points to the right of 177.
Yeah.
So it's 2/5 of that zone. And that zone is 13.5%, right?
Yes.
So there's your answer.
So that is 89.4%.
Okay?
I'm starting to get more confident on these ones, though.
Well, yeah, no, these are pretty easy. You just have to follow the same pattern every time.
Yeah.
In other words, as long as you know that full zone is 13.5%, and that zone goes from 177 to 182, then figuring out what that is, well, that's 5 points there, right?
Yeah.
That's 2 points. So 2/5 of the zone is what you're talking about.
Yeah.
So that's how we got 2/5 times 13.5. These are not easy normal distribution problems. These are as tough as I run across. All right. Number 6. You're good on 5?
Yes, sir, I am. It's just 7 factorial, right? That's it?
Yeah.
Yeah, those are simple. I get those ones.
Okay. Number 6. Write a quadratic equation with a lead coefficient of 1 whose roots are that and that. Well, if those are the roots, then these are the factors. X minus the root. There's one factor. Here's another factor. You with me?
Yeah.
In other words, if they'd have told you the roots are 5 and 7, then you'd have said x minus 5 times x minus 7, right?
Yes.
That would have produced the quadratic. Well, in this case, the roots are complex, but it's still x minus one root and x minus the other root.
Yeah.
Okay, well now that, if I remove the parentheses, I get x plus 1 minus 3i, and I'm multiplying it by x plus 1 plus 3i.
X minus -1 plus 3i.
You see how I got to those two products?
X minus -1 minus 3i. Okay.
Okay, you with me?
Plus 4.
Okay, so those were my roots. This is what they turned into be when I removed all the inside parentheses. Now let's multiply these together and see what we get. And that will be our quadratic.
Okay.
What do we get? First term, let's just do it. There's going to be 9 terms. In other words, we got to multiply that, and then we got to multiply that, and then we got to multiply that, then we got to do the second term, and so forth.
Yeah, we got to multiply a lot of stuff.
Yep. X squared is the first term. I'll get you started. What's the second term?
Plus X.
What's the third term?
3ix.
What's the fourth term?
Plus X.
Always work from left to right. Well, we did all of those. The next one to do is those.
Is 1. So then plus X.
Okay, keep going.
Plus 1 plus 3i.
Keep going.
Minus 3ix. Minus 3i. And that's a negative 9i squared, which is actually a plus 9.
Okay.
Right?
Yep. I'm going to cross that out and make it plus 9. Now, the way these always work is you only have one of those. Now, how many x's do we have? I see one there and one there.
We have 2 x's.
Okay. Now, how many ix's do we have? We have
3ix minus 3ix, which is 0.
Okay, so those cancel. The 3i's, there's a plus 3i and a minus 3i. Those cancel. And the only thing we have left is that plus 1 and that plus 9, which is plus 10. There's our quadratic right there. In other words, if you started with that quadratic and they said factor it, you'd have to use the quadratic formula, and by the time you factored it, you would get these two roots. Minus 1 plus 3i and minus 1 minus 3i.
Okay.
So all we're doing is the reverse. We're multiplying it back together again. But you can't just multiply that times that. You have to find the linear factor, which is always x minus the first root and x minus the second root. So that's how I got these two terms up here.
Gotcha.
Like I said, if they said to you, you got, no, I didn't quite finish this problem. Although it turns out I did accidentally. It says a leading coefficient of 1. Well, that's what we got, was a leading coefficient of 1. So we're done. Had they said a leading coefficient of 2, then I would just multiply this whole thing by 2, and I would get y equal 2x squared plus 4x plus 20. Then I would have a leading coefficient of 2. And that's the way that works. In other words, this is a function whose zeros are these zeros. But if I double everything, those are still the same zeros. Those don't change. If I plug this into the quadratic formula as it is, I get this answer. But if I plug this into the quadratic formula, I get the same answer.
Yeah.
So whether you have a multiple of the equation or not, doesn't matter. You get the same zeros. So that's why they add that a lead coefficient of 1. A more difficult problem would be a lead coefficient of 2. And then this would be the answer. Or a lead coefficient of 3, and this would be the answer.
Gotcha.
Okay. What do we got next, Justin?
I sent you another one.
I think this is it. Yeah, I think this is, oh my goodness, 5 attachments. I'm amazed I got that. Incidentally, if you look at my emails, you'll see I got 3 emails the other night after we signed off. They all came in. Yeah, every email you sent the last time I just got it late. And I guess the moral is that if you want to send me stuff, send it before our session, not during. Because sometimes the internet is just so slow that I don't get them in time. Now, which one of these 5 do you want to look at?
So it would be in that square, the bottom right.
Bottom right. This one here?
Yeah, that's a good.
Okay.
And which is 7, 8.
Because we don't have a lot of time here. But let's have a look. Okay. They love distance, rate, time formulas, don't they? Dirt. They love dirt problems. Help me read this. I can't quite read it.
Adam covered T miles in K hours and then traveled X miles in B hours.
Okay. So, let's put the first part into an equation. How would that go into dirt?
Dirt. So it would be C equals,
we don't know the R yet. We'll just put it in as R. But it's K hours, right?
C equals RK, yeah.
Okay. So that's the equation. And then he traveled X miles in B hours. Doesn't say that he went the same speed both times, but the next sentence does. If he maintained his overall average rate, how long would it take him to go 80 miles? So this R is the same as this R.
Yes.
You think for a moment. So he has to go 80 miles, that's C plus X, right?
Mm-hmm.
So C plus X, if I just add these 2 equations together, I get C plus X equals R times K plus B. If he maintained his overall average rate, how long would it take him to go 80 miles? So C plus X equals 80. Wow. We got a lot of variables here. I don't know how we're going to solve for any of them. Let me think about this problem for a second. So they're asking us to solve for K plus B. Hold on a second. K plus B. I might have taken the wrong path here. So far, I think everything is correct.
Okay.
And that's the general equation for distance, rate, times problems. And it says that he went C miles, that's the distance, in K hours, that's the time. we don't know what the rate is. Well, we know it's c over k. I guess r equals c divided by k. And then we know that he traveled x miles in b hours. So this r equals x over b. And they're the same. So c over k equals x over b. Gosh, there's only 4 variables there, and we have one number to work with, which is d. What is d? 80 miles, and that's equal to the rate, which is c over k or x over b, times the time. Well, the time was k plus b. Is it possible that the answer they want here is not a number but a function? I think that's probably correct. How long would it take him? Well, k plus b. So k plus b, that's the total length, must equal 80k divided by c. That's got to be the answer. See, here's a case where I'm 90% sure that the answer has to be a function of these variables. In other words, they only give you one number, 80. Well, you can't solve a problem with one number. It'd be extremely unlikely. Okay? I got too many variables. I got like 4 variables and they're giving me one number. So there's no way I'm going to be able to come up with a number of hours that it will take him to travel 80 miles. But I know that the time it takes him is k plus b, and time is equal to the distance divided by the rates. So our answer has to be a function of k or c or b or one of them. It looks like I have it as 80k divided by c. I would think that's the answer. But without you having answers, this is a difficult enough problem that, I don't know, the way I usually solve these distance rate times problems, you'll probably notice that I've had some difficulty on some of them. You just have to start with this. You start with that, and then you just try to write out everything you can and come up with equations. Okay? As long as you start with distance equals rate times time. Well, they tell you that he took k hours. Whoops. You know this equation is correct because he went c miles and k hours. So we just don't know what his rate is, but that's still correct. And then he went x miles in b hours at the same rate. So that r is the same as that r. So if I solve for each r, I get, there's his rate. Well, how long would it take to go 80 miles? Well, 80 equals his rate, c over k, times t. And that's what they want, is t. Well, t equals 80k divided by c. That's the amount of time. And it could actually be in terms of b and x also. In other words, r was also equal to x over b. So this might be b over x instead of k over c. And that would also be correct.
Yeah.
But I do not see any possible way how you could come up with a number for this. I think that there's probably lots of numbers. In other words, I don't think there's a unique solution as to how long it would take him to travel 80 miles. It's going to be a function of two different variables. It's going to be k over c or b over x. 80 times b over x, but one of them. That answer or that answer would be sufficient.
That's interesting. Multiple answers.
Well, it is kind of interesting, but when you see a problem that has a ton of variables, know that your answer is usually going to be in terms of a variable. Well, we got one variable there, we got another variable there, we got another variable there, we got another variable there. And they give us one freaking number. So our answer is going to have to be a function of ck, x, or b. And I made it a function of just c and k, which is okay. But we could also made it a function of x and b. Now, whether we can do more than that or not, I'm not sure. I don't think so, but I wouldn't bet my life on it. In other words, I think this is the answer. And what was it? C over k. It was also b over x. I know that. So that's one possible answer. And I suppose what you could kind of do here if you wanted to check your work, and I recommend this to anybody taking the SAT test. When you find a question that has lots of variables in it, you're going to find every multiple choice answer has those variables, or some of them at least. Okay? So how about we make up some numbers? Let's say he goes 8 miles in 1 hour. And then at the same speed he goes 16 miles in 2 hours. Same speed, right? He's averaging 8 miles per hour. So how long would it take him to go 80 miles? 10 hours. Right? Well, let's see if this works. Time equals 80. My b was 2. My x was 16. Bingo. T equals 10. I got the right equation.
All right.
All right, Justin. I don't know how you do it. How do you go to school all day and then put in all these hours tutoring?
You know what? It's helping, and I'm trying to do as good as I can.
Well, I'm sure that it is helping, and I admire your effort. It is a lot of effort. It definitely is a lot of effort. And it pays off. I know. I have my students that will do 4 hours a week, and I can see the results, and then I have students that do a half hour every 2 weeks, and I can see they don't make any progress at all. So the solution is definitely to put in the effort, and you've been doing it for sure. I don't have anybody that's been working harder than you. So I hope it does pay off.
I sure hope so. I agree.
I will talk to you at our next session.
All right. Talk to you later.
All right. Bye-bye, Justin.
Bye.